Now let us understand why is the color of the clear sky blue? The molecules of air and other fine particles in the atmosphere have size smaller than the wavelength of visible light. We have learned about spectrum in our previous session. So, these particles of the atmosphere have smaller size than the wavelength of visible light. These are more effective in scattering of shorter wavelengths at the blue end than the light of longer wavelengths at the red end. So in this spectrum also we can see that one end is red and the another end is blue, violet color, right? So earlier also we have discussed if the particles are smaller, they will scatter smaller wavelengths. If the particles are larger, they will scatter larger wavelengths. Here, the red color has the maximum wavelength and the violet color has the smaller wavelength, which means the particles of the sky of the atmosphere are very small, and that is why instead of scattering red light it will scatter blue light, because we know smaller particles scatter smaller wavelength and blue color has smaller wavelength. That is why we will be able to see the blue color of the sky. The red light has a wavelength about 1.8 times greater than the blue light. You can imagine 1.8 times greater than blue light. Thus, when sunlight passes through the atmosphere, the fine particles in air scatter the blue color, which are of shorter wavelengths more strongly than red. The scattered blue light enters in our eyes. If the earth had no atmosphere, there would not have been any scattering. Then the sky would have looked dark. The sky appears dark to passengers flying at very high altitudes, as scattering is not that much visible at such heights. So, in general, in a very simple language, we will remember that when the sunlight passes through the atmosphere, there are fine particles present in the atmosphere which scatter the white light, and the particles are smaller, so they will scatter the smaller wavelength light, and that is why it will scatter blue light, because the blue color has shorter wavelength compared to red, and as a result this scattering of light reaches to our eyes and we will be able to see the color of the sky as blue. It is so simple to remember and to understand as well. If we think if there is no atmosphere, then what will happen? The answer is if the earth had no atmosphere, there will not be any scattering taking place. As a result, we will not be able to see any color of the sky, which means we may see the sky as dark. So this is all about why is the color of the clear sky blue. I'm sure by now you got the answer. Now let us understand color of the sun at sunrise and sunset. Have you seen the sky and the sun at sunrise and sunset? Have you wondered that why the sun and the surrounding sky appear red? For this, let us understand an activity. We will understand activity 11.3, which is given in your textbook on page number 196. For this, we will need a strong source which is denoted as S of white light, which means that is a source of white light from which the white light will appears at the focus of a converging lens L1. We all know what is a meaning of converging lens. They are convex lens, and convex lens converges the light beam at one point, and that is why they are said as converging lens. Here, this lens provides a parallel beam of light, as you can see in the figure. So, S is light of source and L1, that is our converging lens, convex lens. What to do? We have to allow the light beam to pass through a transparent glass tank, which is T. In the figure you can see which is in blue color. That is transparent glass tank, which contains clear water. Then we have to allow the beam of light to pass through a circular hole which is made in a cardboard. So with this water beaker, you can see a cardboard in which there is a hole which is circular in shape. Then we have a second converging lens L2, and the next is a screen. So what do we have to do? We have to obtain a sharp image of the circular hole on a screen which is MN using a second converging lens. So we have a white source S, L1, converging lens, convex lens, then a beaker filled with water. Then we have a cardboard in which we have made a circle, and then again second converging lens, and then we have a screen. So we have to allow the light beam to pass from all this. So when from the source the light beam will appear, what will happen? The first converging lens L1 will allow parallel beams which passes through the water, and then through that circular hole in the cardboard it will appear to the convex lens, and that convex lens converges that image of hole on the screen. In the next part, what do? We have to take about 200 gram of sodium thiosulfate, which is also called as hypo, in about 2 liter of clean water taken in the tank. So here in the tank we have taken water. In that we will dissolve 200 gram of sodium thiosulfate or hypo. This sodium thiosulfate, which is also called hypo, will look like this. This hypo we need to dissolve in the water which we have taken in the tank. And then we have to add about 1 or 2 ml of concentrated sulfuric acid, which is concentrated, which means strong sulfuric acid, to the water. And then we need to observe. What will we observe? We will observe that fine microscopic sulfur particles precipitating in about 2 to 3 minutes. Now, here the word precipitate we have learned in chapter number 1. What is a precipitate? It is a white solid particle which is insoluble in water. So here we will get precipitate of sulfur, and they will be very fine minute particles of sulfur we will get, and they will be precipitate. Minute precipitate of sulfur we will get in 2 to 3 minutes. As the sulfur particles begin to form, we can observe the blue light from the 3 sides of the glass tank. So, in which tank we have taken water and then solution of this, that tank will scatter blue light. And why is it so? I'm sure by now you all know it. This is because scattering of short wavelengths by minute colloidal sulfur particles. Again, as I said before, that short particles, smaller particles will scatter smaller wavelength, and blue color has smaller wavelength compared to red. This is the reason, again, here we will get the blue color. Why did we get it? Because of scattering of light. Here we will be able to see blue color from all 3 sides of the glass tank, because scattering of smaller particles. Which smaller particles did we get? We got smaller particles of sulfur precipitate. On the other hand, now we need to observe the color of the transmitted light from the 4th side of the glass tank facing the circular hole. Now, here it is very important to know it. From all 3 sides we got blue color scattering, right? But the 4th side of the tank, which is facing to the cardboard, okay, to the circular hole, right, that side will not scatter blue color, okay. Instead, it will be interesting to observe that at first it will show the orange red color and then the bright crimson red color on the screen. What is crimson red color? It is deep, rich red color, which is nearer to violet. Okay. So, 3 sides of the tank scatter blue color, whereas it is interesting to observe that the 4th side, which is facing to the cardboard, to the hole, that will scatter the orange red light and add the last bright crimson red color on the screen. I'm sure that you have the answer. Why is it so? Because all other part will have smaller particles, so it will scatter blue color, whereas here the colloidal particles will not be observed, and because of that it will scatter bright red crimson color, which means from this side the scattering is more because the particles are larger, and that is why it will scatter larger wavelengths. This activity demonstrates the scattering of light that help us to understand the bluish color of the sky and the reddish appearance of the sun at the sunrise or the sunset. The light from the sun near the horizon. What is horizon? The line at which the earth's surface and the sky appears to meet. So, the light from the sun near the horizon passes through thicker layers of air and larger distance in the Earth's atmosphere before reaching in our eyes. Here you can understand it very clearly. The light which is coming from the sun near to the horizon, which is the line at which the Earth's surface and the sky appears to meet, passes through the thicker layers of air and larger distance in the Earth's atmosphere, which means there will be a longer path for the light to come and to reach into our eyes. In the figure, we can clearly see that the sun at noon, at that time, the sun will be overhead, and at the noon time, light from the sun overhead would travel relatively shorter distance. At noon, the sun appears white as only a little of the blue and violet colors are scattered. Near the horizon, most of the blue light and shorter wavelengths are scattered away by the particles. Therefore, the light that reaches in our eyes is of longer wavelengths. So here also we have the effect of scattering of light. Okay, in all these examples we need to remember the meaning of scattering, and we need to remember that smaller particles scatter smaller wavelength which is nearer to blue color, and larger particles will scatter longer wavelength and which appears to red and the colors near to red. Here, why does the sun appears red as sunrise or sunset? So simple. At the sunset and sunrise, the light from the sun has to pass through from many layers. So that is longer part because of thick layers of atmosphere, and there will be larger distance, and we know that the larger particles scatter longer wavelengths. As a result, we will be able to see the reddish color. On the other hand, at the noon time, the sun will be overhead, which means the distance is shorter. As a result, it will scatter shorter wavelength and the sky appears to be blue. Therefore, the light that reaches to our eyes is of longer wavelengths, and this gives rise to the reddish appearance of the sun at sunrise as well as at sunset.